Hello friends, in this video we are going to see loss of energy in pipes. So in this topic, loss of energy in pipe, we are going to see complete flow of fluid through the pipes. Complete flow of fluid through the pipes. So we will be talking here about the losses in pipe, that is your major loss and minor losses. So as an introductory page, look at some of the minor losses in piping system. Minor losses in piping system. So entrance and exit. So whenever the water is flowing through any conduit, at the entry and at the exit there are some losses. At the entrance and at the exit there are losses known as entry loss and exit loss. So these are the fitting loss, actually valves. On the valves also, when the water is passing through the valve, there is the head loss. Head loss means loss of energy per unit weight. Sudden expansion or contraction. Whenever there is a sudden contraction or expansion of the pipe, then also there will be a head loss. Gradual expansion or contraction. In case of gradual expansion and contraction also, there will be loss of head, but in this case the loss will be lesser compared to sudden expansion and contraction. And bends and other fittings. So some of the pipe, it is bent by some angle, maybe 40 degree, 90 degree. So whenever there is a bend in the pipe, this also leads to the loss of head. And any other kind of fittings inside the pipe also leads to the loss of energy per unit weight, known as minor losses. So whatever you have seen in this page, like entrance and exit, sudden contraction and expansion, gradual expansion and contraction, or bends or fittings and valves, all are coming under the category of minor losses, as you can see in the heading, minor losses. Correct. Now minor losses is given by a coefficient k. For example, I want to write loss of head HL. Let us say this is minor loss. HL is equal to V square by 2G. So minor loss is directly affecting the velocity head. But how much? It is 100% or 50%. So along with this velocity head, one coefficient is multiplied. Let us say K loss coefficient KL. KL loss coefficient KL. What will be the value of KL? That depends upon the type of fittings, type of valves. So different valves, different fitments will be having different coefficient of loss. For example, you can see the first one, retrent loss coefficient is 0.8. You can see the flow pattern. So there is this boundary is projected outward. That's why the flow has to turn almost like 180 degree. So their loss is higher on this side, 0.8. Correct, almost reaching near to 100%. But if there is a sharp edge, 90-degree turn, then it is reducing to 0.5. KL reducing to 0.5. If you are making slight curve at the corner, you can see at this corner you are having slight curve, then still slightly rounded, then loss coefficient becomes 0.2, 20% only. And if you are making high radius of curvature at the bend, then you can see the loss is very, very less. The value of KL is 0.04. Correct. So depending upon the design, depending upon the curvature, loss coefficient depends. But it will be multiplied by the velocity head always to count for the total head loss in terms of meter. In terms of meter. Okay. Let's go to the next slide. Loss of energy in pipe. So as I told you, the total loss of energy in pipe can be divided into two categories. One is your major loss and minor loss. Major loss is due to friction. Major loss is due to friction, that we have already seen in the last chapter, that is your turbulent flow. Major loss is due to friction. So friction factor must be there in the equation. HF equal to 4 FLV square by D into 2G. What is the name of this equation? Darcy-Weisbach equation. Correct. So major loss is due to friction given by 4 FLV square by D into 2G. Darcy-Weisbach equation. One more equation is there, that is Chase's formula. That is only for civil engineering. We are going to cover this Chase's formula in the open channel flow. Next, minor losses. Under minor losses, there are so many topics here you can see. So due to case 1 is due to sudden expansion of pipe. So you know the difference between sudden expansion and gradual expansion. Second one is due to sudden contraction of pipe. Contraction and expansion both are just opposite to each other. Then due to presence of some obstruction in the pipes, any solid object will be present in the pipe, that is called obstruction. Due to bend in the pipe, the bend angle may be 90 degree, 40 degree, 70 degree. So whenever there is a bend in the pipe, it will also lead to the losses. Pipe fittings like valves, coupling, jointers, etc. This will also give some amount of losses coming under the category of minor losses. Entry loss and exit loss. So totally we are having 7 different types of minor losses. We are going to see all these minor losses one by one in sequence. Okay, let us start with the first one, due to sudden expansion of pipe. Minor losses in pipe, you can see the first one, loss of head due to sudden expansion of pipe. So the diagram is given very clear here. You can see the diameter D1. Initially the diameter was D1. After expansion, the diameter increases to D2. Correct? And at this section, the velocity is V1 at the entry part, and at the exit, the velocity is your V2 here. So D1 V1 and D2 V2 are the corresponding velocity and diameter at the section 1 and 2. So this is the region of turbulence. Where is the loss actually? You can see the region of turbulence here. Region of turbulence. So because the flows suddenly cannot bend 90 degrees, so it will not cover this area. So there will be backflow and formation of eddies, also known as turbulence. So that is the loss actually, loss area. So how to find the head loss due to sudden expansion? H expansion is given by V1 minus V2 whole square by 2G in meter. Now the question is, which one is greater, V1 or V2? Here V1 is greater than V2 because area is less here. Correct? Area at section 1 is less. So your velocity will be more here compared to the velocity at section 2. Correct? So V1 greater than V2. So V1 minus V2 whole square by 2G in meter. What is V1? Velocity in small pipe. That means velocity in pipe having smaller diameter, and V2 is the velocity of the flow in the large pipe. I mean in the pipe whose diameter is large. Let's go to the next slide for sudden contraction. Loss of head due to sudden contraction of pipe. So contraction is just opposite of expansion, we have already seen. So this blue color arrow marks what you can see here is the velocity profile, which is always constant at the entry section at section 1. And this is the exit section, section 2, velocity profile, which is also constant at the exit part. Now area. This area is A1, and after reduction the area is A2. You can see here A2, and this is vena contracta actually. So H contraction, the formula is different. I told you every time whenever you are going to find the head loss, you will be having velocity square by 2G multiplied by some coefficient. It can be K, or it may be in terms of Cc minus 1. You can see for here H contraction 1 by Cc minus 1 whole square by 2G, V2 square by 2G. Correct? So here V1 is very, very small. V1 is very, very small compared to V2, so it is neglected. V2 square by 2G. What is Cc then? Cc is coefficient of contraction. Cc is your coefficient of contraction. And condition 1, for Cc equal to 0.62. Suppose if Cc value is given 0.62, correct? 0.62. Then if you put this value in the equation 1, let us say this is equation 1. So if you put the value of 0.62 Cc value in equation 1, you will be getting H contraction equal to 0.375 V2 square by 2G. But if Cc value is not given, suppose sometimes if Cc value is not given, then H contraction directly you can write 0.5 into V2 square by 2G. What is the meaning? So V2 square by 2G is the velocity head. So it means that generally what happens, no, 50% of the velocity head is lost during the minor losses. 50% generally. It may go up to 2 times, It may go up to 8 times also possible, but generally it is 0.5 v2 square by 2g. If nothing is given, you can take 50%, 0.5 v2 square by 2g. Okay, we'll go to the next slide to see loss of head due to presence of obstruction in pipe. So this is, you can see obstruction here, solid obstruction in the pipe. Okay, and this is the flow direction, solid obstruction in the pipe, and section 1 1, section 2 2. H obstruction is given by, again, velocity head v square by 2g, the same thing as I told you, into some coefficient. What is that? A by cc into a minus 1 whole square in meter. So what is A? V square root 2g is velocity head, you know that. What is A and capital A and small a? A is cross section area of the pipe, correct? A is the cross section area of the pipe, and small a is the cross section of obstruction, but it is frontal area or projected area. You have to find the projection from this direction, correct? From this direction. So it is frontal area. That means the face which water is projecting or water is moving and hitting the face, that face you have to find the area, frontal area or projected area. And what is cc? Cc is same here, coefficient of contraction. Cc is your coefficient of contraction, and this value will be given to you for calculating the head loss, coefficient of contraction. Okay, we'll go and see the next slide for the next case. Loss of head due to bend in the pipe. So you can see the separation zone here. You can see the separation zone in the pipe here, correct? It is in turbulence separation zone. So what is the angle of turn here? Almost 90 degree here, 90 degree, correct? Loss of it due to bend in the pipe. Look at this pipe also. Flange elbow, flange elbow. So bend is there. KL, what is the value of loss coefficient? 30%, 0.3. And here sharp turn is there, 90 degree turn almost. No curvature is given. So KL is 1.1. Right? So this gives you idea. So what is the difference in the two figure and how the loss coefficient is increasing. And we are talking about this area. Look at this. So the pipe is turning 90 degree with having radius of curvature definitely R. But you can see the loss area, correct? This dark area, you can see this part, correct? Here the loss is this part. Okay, so this is the loss area, direction of turbulence, and it is formation here, and head loss decreases here. So what is mentioned in the point 1? Look at this. Sharp bends result in separation downstream of the bend. Separation means the boundary layer will separate, and that is creation of turbulence. Second one, the turbulence in the separation zone causes flow resistance. So this turbulence, the formation of turbulent zone or turbulence, is nothing but it creating a resistance. Resistance means it will not help you. It will not help you to move in the forward direction. Instead, it will try to drag you in the opposite direction. That means it simply, it simply try to stop your movement, because this turbulent flow, the fluid particles moving in random direction. If you come across this flow, you will also try to move in the random direction. So you are not able to move in a particular direction. So your energy reduces, energy loss occurs. Third point, greater radius of bend reduces flow resistance. Very good point. Greater radius of bend. So higher the radius of curvature, the smooth is the turning. So the losses will be less. What is the formula for finding head loss due to bending? The answer is HB equal to kV square by 2g. Again, it's a velocity head. Again, it's a velocity head v square by 2g multiplied by some coefficient. So coefficient of bending will be given to you. What is K? K is your coefficient of bending, and that will be given in the question. Coefficient of bending. So K depends upon important factor, angle of bend. Correct? K depends upon angle of bend. Higher the angle of bend, higher will be the loss or value of K. Radius of curvature. Higher value of radius of curvature gives you the less amount of losses. The losses will reduce. If you increase the radius of curvature, the loss will decrease. Radius of curvature is good actually. And diameter of pipe. Higher the diameter of pipe, if you increase the diameter of pipe, the loss also increases, because it will create the turbulence. More space is available to fluid particles, then it will try to move in random direction, and this will create the turbulence zone. Look at the next case. For loss of head in various pipe fittings such as valves, couplings, joints, etc. So what are the examples of these fittings actually? Some diagrams are given here. Look at this naming, like ball valve. So you can increase the flow rate with the use of this valve. Angle valve, right? You can see 90-degree angle is there, and this is globe valve. You can rotate by 360-degree globe valve. User defined, number one, user defined two. Depending upon the user, I mean, it is something like customized. One heater is there also, heater in between the flow. 90-degree elbow case, you can see. So these are the fittings used in the pipeline. T run, T branch actually. 45-degree elbow also. It's not, don't think that a pipe is always bent by 90-degree. This is a good example of 45-degree. Reducer, like diffuser, it is a reducer. And gate valve. So all these different types of fittings can be used in the pipe, and which are responsible for creating the minor losses. So each fitting is given by formula V square by 2G, and K is the coefficient. What is K? K is the coefficient of pipe fitting. K is the coefficient of pipe fitting. Now look at this point 5. Loss of head in various pipe fittings such as valves, coupling, joints, etc. Same point actually. So I just given you the example where these fittings are used in the pipeline. So you can see this is the reservoir here having the free surface of water. Inlet, you can see the inlet section here. From here the water is going via elbow and pump and then pipe into the outlet, this reservoir, which is at a higher elevation, right? Which is at a higher elevation. You can see the height of tank. This tank is more compared to the inlet tank, right? So we have to take the water from this tank to that tank 1 to tank 2. So what are the things we have to use? Definitely pipeline, we have to use pump, valve. So these are the fittings actually. Very good example. Elbow, 90-degree elbow is there, you can see. Then pump is also a kind of fitting between the pipelines. A T joint, then valve, and then this is the pipe. So elbow, pump, T, valve. So you can see 4 fittings are used in the pipeline. This will definitely create the minor losses. And finally it is coming in the outlet zone. So H fitting formula is given by K B square by 2G. All the formula is minor losses means velocity head only, V square by 2G, and multiplied with some coefficient K. K will be given in the question always. Don't worry about the value of K. You cannot take from your own. They will definitely give you the value of K. If nothing is given, you can take average as 0.5 V2 square by 2G or V square by 2G. Okay. Let's go and see the next examples. So here we are going to see something about the loss of pressure, minor loss of pressure. Look at this line first of all, then we'll go to the equation. Minor loss is a function of loss coefficient KL and dynamic pressure. Correct? Dynamic pressure. What is dynamic pressure? Half rho V square. Correct? Dynamic pressure. Once again, minor loss is a function of loss coefficient KL and dynamic pressure, that is half rho V square. You can see. So minor loss delta P, that is P1 minus P2 is talking about. What is written in the, let us say I'm writing 1.1, I'm writing here P1 minus P2 is a function of loss coefficient KL and dynamic pressure half rho V square. Okay, that is what it is written here, KL into half rho V square. Now if you want to write HF, head loss, correct? If you want to write HF, head loss, what is HF actually? P1 minus P2 by rho G, correct? So KL is already there, correct? In this equation you have to divide throughout by rho G. So half is there, rho V square. This part is already there, you can see here, KL into half rho V square, and then I will divide by rho G. So LHS and RHS I just divided by rho G in the numerator. So what I can see now, so this P1 minus P2 by rho G is known as head loss, HF or HL, you can write anything. Now KL, loss coefficient. Correct. What I can cancel here? Rho, rho. So I'm getting KL into V square by 2G. This is what I was talking about, that your minor losses equations are coming equal to V square 2G times of loss coefficient KL. Unit will be always meter. Okay. Very good explanation of this equation. Now look at the last second point. Friction factor and geometry factor are very difficult to quantify. Look at this. Friction factor, that is 4F, and geometry factor are very difficult to be quantified for the pipe components. So that the two parameters, which two parameters? Friction factor and geometry factor, are very much difficult to quantify for the pipe component, so that the two parameters, geometry and friction factor, are accumulated into a single loss coefficient KL. So this is a design parameter. Definitely this is done by the scientist and the person who is involving on the study of this friction factor and geometry factor. So after study they will give you the value of KL. So nothing to worry about that. So this KL combines the effect of geometry as well as pipe material, that is friction, and you're using the value of KL in the equation. Okay. Entrance examples are there. Already we have seen retrent, right? Yeah, or reentrant. KL is 0.78. You can see the turn is almost 90 degree, 0.78, almost near to 80% also we have seen. Here you can see there's a 90 degree turn here, 90 degree turn here, sharp edge. So KL is 0.5. So from 180 to reduce to 90, and it is very smooth. You can see radius of curvature is given here. Smooth curvature, rounded KL depends upon roundness. Correct. So if your roundness is more, your KL value will decrease. Right. If your roundness, if you are increasing the roundness in the pipe, then your KL will reduce. Okay. When the fluid flows from a pipe into a tank, it mixes with the fluid in the tank and eventually comes to rest. The exit loss is the entire fluid kinetic energy, that is KL equal to 1.0. In the exit loss, always you are using KL value equal to 1. In the last slide, we have seen the entrance loss, right? All the losses were entrance loss. You can see entrance, it is written 6, right? Examples A, B, C. Entering into the pipe, and this is the exit part. Okay. So 0.78, 0.5. But what is in the exit? You can see in the exit, when fluid flows from a pipe into a tank, it mixes with the fluid in the tank and eventually comes to rest. Correct? Because whatever be the velocity of the water in the tank, it will come to the same velocity, that is rest. The exit loss in that entire fluid, the exit loss is the entire fluid kinetic energy loss actually. So that's KL equal to 1. So whatever be the velocity head, V square by 2G, complete loss of velocity head. So KL is 1. So this is the exit streamlines you can see here. So reentrant KL value is 1.0. Sharp edge 90 degree. Sharp edge at KL value again 1.0. Rounded also KL 1.0. So whatever be the case, whether it is 90 degree or 45 degree or even smooth curvature is there, the loss of head coefficient KL will be always equal to 1 in case of exit losses, in case of water exiting from the pipeline. Okay. Thank you.